This video will set up an integral representing surface area for a parametrized surface. The surface we're going to look at is S is given by the equation y is equal to 9 minus x squared minus z squared. Though that object is actually infinite in size, so that would have infinite surface area, we need to cut this off at some point. So we're only going to look at the part where y is greater than or equal to 0, and we're only going to set up the integral and not actually evaluate. This surface is actually a sideways paraboloid with y going between 0 and 9, and you can kind of test that by if you had picked appropriate values of x and z so that the sum x squared plus z squared would equal 9, then you'd have 9 minus 9, and that's our cutoff. When y is actually equal to 0, go ahead and plug that in. You'll see the equation x squared plus z squared is equal to 9, so that's a circle of radius 3 in the xz plane. Here's a parameterization. Realizing that you have circles in the xz plane, I went ahead and used, I sort of thought about polar coordinates in the xz direction, so to speak. That's why I have u cosine v and u sine v. And if that's nice parameterization for a circle of, excuse me, a varying radius u, and v will sort of represent theta, in the xz plane, then you can see that y is completely determined. All you have to do is plug in 9 minus u cosine v quantity squared minus u sine v quantity squared, and you'll just get 9 minus, well, I shouldn't say r squared, but here 9 minus u squared. And the parameter domain, what is u? U just goes from 0 to 3, so we're going to get the smallest, tiniest little circle, which is a point, all the way up to a circle of radius 3, and all radii circle in between, and v goes from 0 to 2 pi. If you don't really trust me, you can try different parameterizations, but here it is in the app for parametrized surfaces. You can kind of roam around on this thing and see, here's the red grid curve that shows you what happens for various values of v. So v again is sort of to be thought of as the angle in the xz plane here. And for various values of u, you can see what u does. U is supposed to be simultaneously the radius of the circle. That's why u cosine v, u sine v, the u in front. But u is also, well, close to the difference between so u squared and v should add up to 9. So there's this sort of quadratic relationship, and this, you can see here that the smaller that u is, the bigger y should be, right? So let's take a look, right? So small u is like over here, and that's a much bigger y value, kind of closer to the value of 9. But a bigger u value, like 2.5, then you have 9 minus 2.5 squared. That should be a smaller value of y. Yet, what about the radius of the circle? Looking from the projection direction of xz, this should be a circle of radius 2.5, because all you do is you plug in 2.5 for the u's. And now let's go back. So I took the derivative with respect to u, I also took partial derivative with respect to v, and the cross product, if you write out all the details, looks like this. We are going to need the length of this vector, so the magnitude of that vector looks like this, and I simplified just slightly to get something like that. So what is the area? Well, we need to plug in to this formula, so we need d, the parameter domain, u went from 0 to 3 and v went from 0 to 2 pi, and then this little piece, the norm of the cross product we had just computed earlier, is right there.